So to start with, we're going to look at 4 simulations. So as usual, you go to the 1100 folder, and you want to go into the Lab 4 folder. And there's 4 simulations. So let me open up the first. When you click Run, what this is going to do is it's going to show us a little movie of a ball moving on a string in a circle. So I click Run, and you see it moving in a circle now. Now the program keeps track of the x and y components of the velocity and also the magnitude of it. So at any point I can stop this, and you can read off the values for the x component, the y component, or the magnitude. And they ask you some questions about this. So they say what's happening with the velocity components and what's happening with the magnitude, the speed. They also ask you about the velocity vector, so that arrow that's attached to the speed. And finally, the most important question, why do we say that this object is accelerating? Because I can stop the motion at any point, and the magnitude is always 2 meters per second. So how come, if the speed is always 2 meters per second at any point in the motion, we say that this object is accelerating? Hint, hint, I said speed, not velocity. Think about that. After you've answered the questions, you can go on to the next simulation. And again, this is going to show us a ball moving in a circle. So right now you can already see the velocity vector. As soon as I click Run, it's going to fill in the acceleration vector also. So now you see the acceleration on there as well. And they ask some questions. So what direction is the velocity vector pointing, and in which direction is the acceleration vector pointing? Now that means relative to the circle, given that this is moving around constantly. In the manual, there's also a snapshot of 1 moment in time for this motion. And they want you to draw in the directions of the velocity and the acceleration vectors at that 1 moment. They also want you to say what direction they both point in relative to the circle. So it's useful to use phrases like tangent to the circle or toward the center when you're answering that question. After you've answered those questions, then you can go on to question 3, which is actually not a simulation. So I'm going to show you a separate little bit of video for that, and then I'll come back and show you the next 2 simulations. So in question 3, you need to do a vector subtraction, but it needs to be a graphical vector subtraction, and not everybody's classroom instructor shows them how to do this. So I'm going to show you here so that you can do question 3. So this is the diagram that you're given in your lab manual, and what it is it's supposed to represent an object and the velocity vector at 2 different times. So when the object is located here, the velocity vector points in this direction, and a little while later, when the object is located here, the velocity vector points in this direction. So the velocity vector changes direction over time. And you want to do a graphical subtraction. So what that means is that you need to take this first vector, the VI vector, and you want to redraw it in a new location. Specifically, you want to redraw it over here, tip to tail, with the final velocities vector, so the VF vector. And you may want to do this by hand with a ruler and a protractor, because what's important is that when you redraw this VI vector, you have to draw it the same length and the same angle as it is right now. So like I said, you may want to do this by hand, but I can do it really easily with the computer. So I make a clone of it, that red vector, and like I said, it's got exactly the same length and the same angle as the original VI vector. And then I'm going to grab this, and I'm going to move it over here so that it's tip to tail with the VF vector. So you'd be doing this yourself, where you redraw that vector, same length, same angle, but tip to tail with the VF vector instead. Now, because this is actually supposed to be a vector subtraction, the direction of the VI vector that I redrew should actually be pointed in the opposite direction. And again, I can do this really easily on the computer. So now that arrowhead is pointed in the opposite direction. So once you've done this, the graphical vector subtraction just consists of finding the vector that connects the VF vector and the redrawn VI vector. And so that's what I'm drawing in here in blue, that little tiny vector that connects the tip of the new VI vector to the tail of the original VF vector. So you just connect the two with a new vector, and that new vector tells you the direction that the acceleration vector points. And if you've redrawn your VI vector carefully, that vector should point towards the center, which is what we expect for uniform circular motion. The acceleration vector should point towards the center of the circle. So that's what you're demonstrating in this question. By moving the VI vector over and showing the vector subtraction between them, which again is that blue arrow, you're showing that the direction of the acceleration points towards the center of the circle. So that's how you do question 3. So now you're ready for simulations 3 and 4. So I'll open up simulation 3. And again, we've got balls traveling in a circle, but there's 2 of them now. And notice that the radius is the same for both of these balls, but one of them has twice the speed of the other. So this one has a speed of 2 meters per second, and this one has a speed of 4 meters per second. Now when I press run, the balls are going to start moving and the program will fill in the acceleration vectors. That's what we want to look at for this question. We want to look at the acceleration magnitudes and see what happens when we double the speed of something. So I'll click run. Immediately we see that one of these has a large acceleration magnitude and one of them has a small acceleration magnitude. So the question is, what happens to the magnitude of the acceleration when we double the speed, but keep the same radius? You specifically want to look for obvious proportionalities. So did the magnitude get twice as big? Is it half as big? Is it 4 times as big? Look at the exact numbers and see if you can figure out what the proportionality is. When we double the speed, but keep the same radius, what happens to the acceleration? The next question asks, does the acceleration vary directly or inversely with speed? And I'll warn you that as worded, that's a little bit of a trick question. So you might want to look up the equation, what it's supposed to be in the pre-lab, and then see if you can figure out what the trick here is. The last question says, based on this simulation, suggest an equation or proportionality statement that relates acceleration to speed. So what they want you to do is to write down A is proportional to, and then write down some function of V. So the acceleration is proportional to what sort of a relationship with V. So you write that down, and then you're ready to look at the next simulation. Now this one looks very similar, but in this case, the 2 balls have the same speed. They're both moving at 2 meters per second, but one of them has half the radius as the other one. So we've halved the radius, but we're keeping the same speed in this case. So again, we're going to click run and look at the magnitude of the acceleration vectors and see what changed. So I click run, and we see our magnitudes, and we can see that they're not the same size anymore. So again, you're going to look for a rough proportionality. So when we halved the radius, did the acceleration get twice as big, half as big, 4 times as big? Figure out what the proportionality is. And again, they ask you whether the acceleration is directly or inversely related to the radius. And they want you to write down a proportionality statement again. So again, you'd write down A is proportional to, and then in this case you write down some function of R instead of V. And then the next question after this will ask you to tie everything together and write down one equation that relates acceleration to both speed and radius. Hint, hint, this should look pretty similar to something you saw in the pre-lab or maybe even in class. And then finally, using algebra, you're going to check that the units work out to be meters per second squared. In other words, the units for an acceleration. And then you're ready to move on to the next part of the experiment. So this is the apparatus we use. We've got a platform that spins, and mounted on top of that, we've got this sensor that is going to allow us to directly measure the acceleration that comes from the fact that this apparatus is spinning. We also have a photo gate over here that is set up in such a way that this sensor is going to block it on its way past. We're going to use that fact to measure the period of rotation of the apparatus. So the period of the spin is the time it takes for one complete revolution. In this experiment, you want the timer to be set in pulse mode, so that's 2 clicks up from the bottom here. You also want it in read mode, which just means click this downward, the light will be on. When you've got it set up like this, what's going to happen is that if you pass an object through the photo gate one time, it starts the timer, and it doesn't turn off until you pass something through a second time. It's also set up so that you can't trigger it more than once. So if you need to take new data, you press the reset button, that zeroes it, and then again, going through the first time turns the timer on, going through it a second time turns it off, and you can't trigger it after that. So this is good for measuring a period of rotation, because when something triggers the photo gate the first time, it'll start the timer. When it comes around and triggers it a second time, that's what turns it off. So you'll have measured the period of one complete revolution. So when you give this a spin and push the reset button, the photo gate is automatically going to be turned on and off because we've set up the timer correctly. Now, there's 3 things that we're going to need to measure with this apparatus in order to theoretically predict and experimentally measure the centripetal acceleration. To theoretically calculate the acceleration, you're going to need 2 of those quantities. One of them is the radius of rotation, and the second is the angular velocity of the spin, which we're actually going to calculate from the radius and also the period of rotation. The radius of rotation is measured from the center of this hole over to this little figurine that's been taped onto the top of your sensor there. So you would grab a ruler and measure the distance from your figurine to the center of the circle. Now, not every technician will put the little figurine on here, so if your device doesn't have the little man, that's okay. There's a little dot on the top of the sensor, just above the on button, so right above it, a little dot that says XYZ, and that marks the internal location of the sensor. So you can measure your radius from the center of the hole over to that little dot that's just above the on button. The second thing that you need to measure in order to calculate your theoretical acceleration is, as I said, the period of rotation, which you get with your timer, and I'm going to show you how to do this in a moment. And finally, the third thing you get is the acceleration. So the experimental acceleration measured directly by this sensor, which is done in conjunction with a computer program that I'm going to show you in just a moment. Now, there is one thing that is tricky about the data taking in this experiment, and that is that you need to measure the acceleration with the sensor at exactly the same moment that you measure the period of rotation here. The reason why is that there is actually friction in this system. In fact, you'll see that on screen when I show you the computer program. And because there's some friction, that makes it important that we measure the acceleration at the same time that we measure the period. Otherwise, our experimental value and our theoretical values may not agree with an uncertainty. So, before you start taking data, there's two things you should do. The first of them is that you need to level the apparatus. So that's what this spirit level is for. You put this on the base, so not the spinning part, but the base. And you want to get up high and look straight down on it, and make sure that the bubble looks like it's centered in that circle. If it doesn't, these little legs, the bottoms of them are screws. So you could screw the little black part back and forth, and that raises and lowers that leg. So there's 3 legs on here. You can adjust the feet of the apparatus to level things. And as I said, you look straight down and make sure that the bubble looks like it's centered in the circle. The second thing that you want to do is turn on the sensor. So you need to do this before you connect the sensor wirelessly to the computer program. And so to do that, you just push the on button and hold it for about 5 seconds. And that's all you need to do to turn it off as well. So it'll start blinking red when you first turn it on, and after we get it connected to the computer program, that red light will turn green. Another thing you want to do is take note of this ID number written right here on the sensor, because when we want to connect the sensor to the computer program might actually pick up everybody's sensors in the whole room. So you'll need this ID number to connect to your sensor specifically, rather than somebody else's. So level your apparatus, turn the sensor on, and make note of the number written right here on the corner. So now I'm going to show you the computer program and how you take your data. Now for this experiment, we're not going to go into the Physics 1100 folder. Instead, you want to look around on the desktop for a program called Vernier Graphical Analysis, and open that up instead. So that looks like this, and on this first screen, you want to choose Sensor Data Collection. So click that first link, and you give it a moment to hunt around for wireless devices. And the thing is, it could pick up all the wireless sensors in the whole room, so this is why it's important to have that ID number for your sensor. So go and find your sensor in the list according to its ID number, and when you find it, then you click Connect. And then once it finds it, there's one more thing we have to do on this screen. So right here, where it says Sensor Channels, right now the sensor channel is set to force. We don't actually want that, so click this side arrow to expand the list of sensor channels. And what we actually want is the x-axis acceleration. So turn off force and turn on x-axis acceleration. Then you can click Done. And there's one thing you should do before you take data, and that is down here, if you click this button, you have the option to zero the sensor. You should do that. So you click this button and then click 0, and that'll zero your sensor. So you want to do that when the sensor's not moving. So now I'll take some data. I'll click Collect, and then I'll give the platter a bit of a spin. And one thing you'll notice right away is that this is not level. It's got a downward slope to it, right? So we're measuring the x-axis acceleration. So that's our experimental acceleration. We're measuring it directly. But the acceleration was bigger at the beginning of the motion than it was at the end. That's because of friction. So there is friction in the platter, and we can see that in our data. The acceleration is slowly getting smaller over time. So to deal with that, we're actually only going to take about 1 second's worth of data, and we'll get our average acceleration from that 1 second of data. So that's listed here under the statistics. However, it's important that we hit the reset button to measure the period of rotation at the same time that this data gets taken. So the way in which you do that is choose one of these vertical lines on the graph. Just pick one. I'm going to use this center one here. And I'll start taking my data, and when the data comes across and crosses that vertical line that I chose, then I'm going to hit the reset button. And that way, later, when I highlight just 1 second of data after that point, I know that I'm going to be getting the acceleration that was measured at the same time that the period of rotation was measured with the photo gate. So I want to show you this, so I am going to resize this a little so that you can see what's going on with the equipment at the same time. So I'm going to give this a spin. I'll click collect, and I'm going to wait until the line crosses that middle line, and then I pressed my reset button. And so now this period of rotation was taken at the same time as this area, the data. So I highlight just 1 second of data here, and then to get the mean value, the average value, I go down here to the little graph icon, click on that, and then click View Statistics. And that gives me my mean acceleration. So that'll be my experimental acceleration value. And it got measured at exactly the same time as this period was, which is important because that'll give me my best chance of getting good agreement between my experimental acceleration and my theoretically calculated acceleration. This is the graph that you'll want to put in your report, and that means you're going to need to print this somehow. Now the problem is that this program doesn't actually let us send the image directly to the printer. So the easiest way to print this off is look around on your keyboard for the button that says Print Screen, click on that, and then you can open up Word, and you can paste the image into Word, and then print out as many copies as you need for your group.